Continue talking about concavity and second derivatives and all that goes with it. We're going to go through whatever we can in the notes. I may skip some along the way, just definitely going to skip some along the way because there's no way. So I've got some problems that are good ones to skip over. But I believe we're ready for the bottom of this page, 293 here. Explore the possibility that a graph could change concavity at a discontinuity. Say a vertical tangent line, or probably more importantly, where the second derivative does not exist, such as at a cusp or a hard point. In case of a vertical tangent line where the x value is not in the domain of the function, then the value x equals p will not be an inflection point. So we have a few examples of where there may or may not be inflection points. So on the left side, we have examples of there is an inflection point there. So we talk about there is an inflection point there at P, because notice to the left of P it is concave down, to the right it is concave up. Okay, and that's more your traditional problem. That is just where the second derivative would equal 0. Okay, now look below it. If you look to the left of P. To the left of P, what kind of concavity do we have? That is concave up. To the right, we have
Down.
concave down. Does inflection change or concavity change there? Yes, so that makes it a inflection point now. However, what about the derivative at that point?
It doesn't exist.
It doesn't exist, right? It doesn't exist because that is a cusp. Okay, on the right side, now we're looking at when there is no inflection point. So if you look to the left of P, what kind of concavity do we have to the left of P?
Up.
Concave up. To the right of P?
Up.
Concave up. So notice, concavity did not change. So is that inflection point? No. And what is also true about the second derivative?
And the cusp.
Yeah, and so this is, in a way, no different than the last one where the second derivative is not going to exist, but yet it is because concavity does not change. So these are some, special cases. Last one. Concavity to the left of P is concave up. To the right of P, concave down. You have, how do I want to say this? You have concavity changing, however,
It's not continuous.
it's not continuous. That x equals p is a vertical asymptote. Okay, so with that x equal p being a vertical asymptote, it's not, with it not being continuous, we can't talk about there being an inflection point. Okay, and again, it's different, but the second derivative, again, does not exist. This time it does not exist because it's a vertical asymptote. Okay? So there's always these special cases, right? It's always nice when they give us the nice normal problems that work out nice and neat, but we've always got the special cases as well. Okay. As we look at the next page, we're going to talk about sign charts here. So we'll use a second derivative sign chart to determine intervals of concavity, as well as actual inflection points. The possible points of inflection can be called the critical values, and this should say critical values of f double prime there. Okay, they are possible points of inflection, and that is of f double prime. Remember, concavity can change at a discontinuity, such as a vertical asymptote, just demonstrated that, but it won't be an actual inflection point. In order to classify an x value as an inflection point of a function f of x, the x value must be in the domain of f of x. And so thus the idea of continuity. So, example 3. Determine any points of inflection and discuss concavity of the graph f of x equals x to the fourth minus 4x cubed. So, what you got here?
4x cubed minus
Okay. First derivative, 4x cubed minus 12x squared. Okay. What about the second derivative?
12x squared minus 36.
Roll. What are you? Oh,
She is mismultiplying is my guess. I don't know. Okay, second derivative, 12x squared minus 24x. Now, our job is to find our critical numbers. We're trying to discuss concavity. So how are we going to find our critical numbers? Our possible points of inflection? Set what equal to 0? The second derivative, yes? Okay. So 12x squared minus 24x equal to 0. How would you like to solve?
12x minus 2.
Okay, GCF, 12x, x minus 2. Setting each factor equal to 0, we get the results of x equals 0 and 2. Okay. X equals 0 and 2, what are those? Those are your critical numbers of the second derivative. And so what they have set up here for is, this is our number line. I know, I couldn't tell at first either. This is our number line. So we're going to put our critical numbers on here, which are 0 and 2. And then we're going to pick some test values, yes? Okay. And we want to know what is going on here. So what would be a good test value to the left of 0?
-1.
-1. So since it says test number, I'm going to write it up here. You guys know I don't really care if you write the value. You know, you don't have to tell me what you're using as a test value. But if we plug -1 in, best place to plug it in is probably, I would use that factored form right there. Okay. Not that you couldn't plug it in anyplace else, but that's going to be the easiest math. 12 times -1 is a negative. -1 minus 2 is a negative. A negative times a negative is going to result in a positive. So what does that tell me? If it's positive, it is concave up. Whether you,
I don't like how they handle
I know. Okay. What about between 0 and 2? Plug in 1. 12 times 1 is a positive. 1 minus 2 is a negative. Positive times negative is a negative. So we have a negative second derivative, which means concave down. And a number to the right of 2?
3.
3. 12 times 3? 3 minus 2. Positive times positive? Positive. This is a positive second derivative, so concave up.
It's like 2 smiley faces and a frown face.
Okay, let's see. What all do we need to discuss? Determine any points of inflection and discuss concavity. So, points of inflection. What points of inflection do we have? Now, based on what I have written, I agree. The points of inflection, they occur at 0 and 2. What would be the actual points, though? You'd have to plug 0 and 2 into the original equation. So you would need to find what f of 0 is and f of 2 is, which f of 0 is easy, yes?
0.
0 minus 0. And again, these are originals, yes? 2. 2 to the 4th is 16. Minus 4 times 2 to the 3rd. 2 to the 3rd is 8. 4 times 8 is 32. 16 minus 32 is negative 16. So points of inflection occur at not P, I started right, P of 0. F of 0 equals 0, and F of 2 equals negative 16. So that we determined any points of inflection. Discuss concavity. What can you say? F of x is, where would you like to start?
Concave up.
Okay, Mario picks concave up. When is it concave up?
Negative infinity to 0. And 2 infinity.
Negative infinity is 0, and 2 to infinity.
The second derivative.
The second derivative is greater than 0.
Because the second derivative is positive, aka greater than 0. Okay? So that leaves f of x is concave down, 0 to 2, because since
That double prime is what?
F- double prime is less than 0. And whether you write f double prime or f double prime of x, small detail, it doesn't really matter, to be honest. Okay, you got the basics? Okay. Example 4. Find the inflection points and the open intervals of concavity and justify. I would say skip this one because it's similar to last time, but you guys always need trig practice, so trig, here we go.
1/2 cosine x is the first
Second derivative is just this.
Okay, first derivative, g prime of x, 1/2 plus cosine x. Because we were trying to talk about inflection points on the open intervals of concavity, we're going to talk second derivative. Second derivative is negative sine x. Good there. Okay, how do we proceed? Set our second derivative equal to 0. So it starts off as negative sine x equals 0. Probably a better way to write that would be to say positive sine x is equal to 0. Just think divide by -1, multiply by -1. Our brains are going to process, my brain, let me not speak for you, my brain's going to process better when does sine equal 0 than when does negative sine equal 0. Just saying. Okay. When does sine equal 0?
Pi and 0 and 2 pi.
Okay. Now, be specific in terms of what's my interval that we're working on, yes? 0 to 2 pi, and notice as it's stated, endpoints are included, right? As this is stated. So 0, pi, and 2 pi based on what's stated up there. And so my brain, and I know this is not what you guys do, but my brain knows that the sine curve looks like this. Okay?
Mountain Valley.
So, okay. Now, with that in mind, what do we need to do here?
You make your chart.
Okay, let's talk sine chart.
Wait, do we have to since we already know what this sine graph is?
We need to make sure it makes sense.
Oh.
Because here's the deal. While you know, well, this isn't my original graph, though. It's 1/2 x plus sine x is the original graph. When we're talking concavity, that's the graph we're talking concavity of. Besides the fact, the second derivative was actually negative sine x. And negative sine x would be that, Valley Mountain.
That's the same.
Second.
Same inflection point, but not same concavity.
Yes.
So, but Regardless, the original function is different. Okay, so if we actually, here's the deal. I just put arrows on the end. Should I have arrows on the end?
No,
No.
because you're on a closed interval.
0.25.
Okay, we are on a closed interval. And with that closed interval, what are the ends of my interval?
0.
0 and 2 pi. And then what's in the middle is pi. Okay, are you with me there? Now, I know normally we go infinitely in either way, but we're on a closed interval. That's what makes the difference here. Okay? Yeah, if they didn't give us a range, we would have to test something outside of the 0 and the 2 pi as well. Okay, so again, excuse me. Remember, this is the second derivative. So we're going for right here. Between 0 and pi, if you plug in a value, so, and not that you have to write it down, but if we plug in pi over 2, because that's an easy value between 0 and pi, right? We want to talk negative sine of pi over 2. So, and here's the deal. Do I need to write this out instead? I don't know. Whoops. That was weird. However you're doing this, right? So sine of pi over 2 is 1. The negative of that makes it negative 1. So here we're going to be talking negative, and negative is concave down. What about between pi and 2 pi? 3 pi over 2 would be the obvious plug-in. What do we know about the sine of 3 pi over 2? It's negative, but the negative of a negative is a positive.
Concave up.
So this is concave up. Okay. Now, with that in mind, let's talk inflection points. Find the inflection points and open intervals of concavity. What about inflection points?
We gotta plug pi.
We need to know what g of pi is. G of pi, so 1/2 times pi plus sine of pi.
It's just pi over 2.
So that's pi over 2 plus the sine of pi is 0, so pi over 2. Sorry, I just wrote a big long equals, equals, equals. I
That's okay.
don't normally do that, but okay. So inflection point at g of pi equals pi over 2. And why is that an inflection point? I guess we didn't state this on the last one, but let's state it here.
As it goes from positive to negative. Or negative to positive.
Okay, so there's an inflection point at g prime, or g of pi equals pi over 2, because g double prime of x changes signs from negative to positive. And you could just say changes signs probably, because it's not going to matter which way, but changes sign from negative to positive. Okay. And then asked us for open intervals of concavity. G of x is
Negative.
concave down then. Where?
From 0 to pi.
From 0 to pi, since
G double prime is less than 0.
okay, since your second derivative is negative, so g double prime is less than 0. G of x is concave up.
Pi to 2 pi.
Pi to 2 pi. Since G double prime is
Greater than 0.
greater than 0.
I did it.
Would you put
Sure.
a graph for
Yeah.
I did not because it asked for open intervals of concavity. Otherwise, they tend to, on something like concavity and increasing, decreasing, do open intervals. Okay,
We still have 4 pages.
I know. Well, I have a couple that we're probably going to skip, so, and we just may, who knows. Moving along. Okay, let's do 5. I have 6 as a possible skip, so probably going to skip 6. Use a calculator, your favorite words, right? Use a calculator to find how many times the graph of y equals x squared minus 3 plus sine of 2x minus 1 changes concavity on the interval 0 to 2 pi. Now, FYI, we're not graphing the original here. Okay, that's not the plan. Okay, so, concavity. What do you need to think?
derivative?
Which derivative?
Second.
Okay, so let's start with the first derivative.
2x plus cosine 2x minus 1
Times 2.
So 2 cosine.
Okay, pause. Let's make sure we all are good there. The derivative of x squared, 2x, minus 3 disappears. The derivative of sine of something is cosine of something times the derivative of something. The derivative of 2x minus 1 is the 2 that I threw out front.
That was chain rule, right?
That was chain rule, yep. Second derivative.
2 minus 4 cosine 2x
Okay.
Minus 4.
Yeah, because you have to derivative.
minus
Oh, it's dang
Okay, I'm there. Give you guys a moment to get there. Obviously, the derivative of 2x is 2. You're there on that part. The derivative, so officially this 2 carries down, yes. The derivative of cosine of something is going to be negative sine of something times the derivative of something. So times the derivative of something is going to be times another 2. And that's where the 4 came from. Are we better there? And write down as many steps or as few steps as you want, something like that. What are we going to do?
Graph
it.
it.
Set equal to 0. So if we think about saying this equal to 0, 2 minus 4 sine of 2x minus 1, that's going to be where we end up with our concavity points, right? Now, and this is where you're looking like, yeah, solving that. I can subtract the 2 over, divide the negative 4 over, and it's doable, but not the most fun either. So, at this point, we are going to graph, okay? So we're going to graph our second derivative, okay?
No. Oh, wow. Interesting.
Now, as you graph this, looks something like this. Recommendations.
2 pi.
First of all, one thing that's going to be helpful, I'm just on a Z standard screen, right? 10 by 10. One of your options in your Zoom screens is a Z trig. Now, what I like about Z trig is right there, those are going through weird values. Like, those aren't, like they might be going through nice things like pi over 2 and pi, but it doesn't look like it. So the thing I like about Z trig, number 7, is that it gives me an idea of where it is in relation to our tick marks. Okay, Z trig is a little zoomed in, but I can see what I need. Now, what's my interval we're talking about? 0 to 2 pi. I heard some of you already talk. Should you change your window?
Yeah.
Yeah, because all we care about is from 0 to 2 pi. So I'm going to put my x min as 0, my x max as 2 pi. And I'm going to hit graph again.
That's cool.
Okay. So, recommendation there, and you could do this without Z-trig, but I definitely would do min and max of 0 and 2 pi. Yes, that's a definite. And I guess that should be specific x min and x max. Okay. How do we answer this question? Use a calculator to find how many times the graph changes concavity. What did we just graph? We just graphed the second derivative, yes? So we're looking at how many times does the second derivative equal 0 and change sign? And that is how many times? 4 times. Okay, we know that because second derivative has 4 zeros. And you can also 4 zeros, and at each of those zeros it is changing sign, yes?
Mm-hmm.
Okay. Now, with that in mind, why do I have that written in? I'm not going to waste time on it. If I asked you to find the points of inflection, what would you do?
0.
You'd find your 0 4 different times, yes? Okay. For some reason, whatever reason, I have that written down there in parentheses. I don't think it's necessary to take our time to do. You guys know how to find zeros. Okay. Number 6, I have in my notes to skip, and I see why. It's pretty much the same type thing we just did, right? It says using a calculator, so you're still going to find your derivatives, and then look for how many zeros, yes? Can I skip?
Yes.
Okay. Well, I don't even know why I'm asking. I'm skipping. Unless you have some, I want to do this
I want
because.
to do it.
Nobody asked.
Because you want to be difficult. Ignored. Okay. On the bottom of this page. Okay. Talks about using the second derivative to find extrema of a function. So, similarly, the second derivative is the first derivative of f prime of x. Okay? So the second derivative, it's another derivative, right? So it's the derivative of the first derivative. So the same relationships that exist between f and its derivative must also exist between the first derivative and the second derivative. So we can use the second derivative test, and it's an alternative method for locating relative extrema. So for finding mins and maxes. With that in mind, if c is a critical number of f, then f prime of c equals 0 or does not exist. This makes x equals c a possible max or min value of the function. Now, let's see, what are we filling in here? If the second derivative is positive, what do we know about the original function?
Positive.
It's increasing.
It's concave up.
There we go. If it's a second derivative, and that's, you have to watch it what we're relating here, yes? A positive second derivative tells me that the original function is concave up. What does it tell me the first derivative is doing?
Increase.
There's the increasing. Okay? I think you can get the next row then, yes? If my second derivative is negative, f is concave down. And the first derivative is decreasing.
I'm guessing that. Zero.
I would say inflection.
Well, okay, so when we talk neither, what are the neither options? If the second derivative is not positive, it's neither. It's either what?
Zero.
0 or D and E. That's not what we're filling into these pieces. Okay, we're talking about the looks of the graph here. So if your second derivative is neither, so it's 0 or D and E, what is possibly happening in the original graph?
It's an inflection.
This is a possible point of inflection. Is it guaranteed? No, not until you do a little check. But it is a possible point of inflection. Okay? If my second derivative is either 0 or D and E, what does it mean about the first derivative?
Min.
A possible min or max. Okay? Because think about it, if your first derivative is increasing or decreasing, what happens between increasing and decreasing sections? Mins and maxes. Okay. Continuing along with whatever we can here. On this page, I have that I'm doing 7 and skipping 8. And realize anything I skip, is it in the notes on Schoology? It is, but I'll tell you right now, I know that they're not available yet because
What the heck is this, Sergeant?
slacking.
Yeah, right.
Okay. So, oh, actually, you know what? 7A and B. And based on the fact that we're skipping B, it would be smart for me to just zoom in A, wouldn't it? Use this whole screen. Use the second derivative test to find the relative extrema for each function. Justify. Okay, so
First derivative.
start with the first derivative, of course.
4x cubed
Minus
minus 24x squared.
Now, okay, that's my first derivative, yes? With the first derivative, what we're doing here is we're trying to find extrema, yes? But we're trying to use the second derivative test to do this. Okay, so we do still need to find, unless I'm mistaken here, we do still need to find our critical values. Yes. Okay, so if we go ahead and find our critical values here. 4x cubed minus 24x squared equal to 0. What's happening? Factor out of 4x squared. Factor out 4x squared, you're left with x minus 6. If we set each piece equal to 0, what do we know?
X equals plus or minus 2. X equals 6. Oh no, I'm so sorry.
0.
X equals 0 and X equals 6.
Okay, I totally see where you went. However, 0 divided by 4 is 0. Okay, and what are these right here?
Critical.
Those are my critical, I'm going to say numbers, just because they're not ordered pairs yet, but yeah.
Is values okay too?
Yeah. Now, with this in mind, let's see. Yeah, I'll come back and find them later. With this in mind, if we start talking about like what they're filling in here, x equals c, our critical values are 0 and 6. Why there's not a line dividing that? Got nothing. Okay. I guess if I go with filling in this chart, what is f of c? So
Negative.
f of c would be plugging in 0 and 6, right? And finding what f of 0 and f of 6 is. I'll take 0, you guys can have 6. 0 to the 4th minus 8 times 0 cubed minus 5 is negative 5.
I wanted 0.
Too bad.
No,
I
me
need
too.
0.
I'm the teacher. I get to pick. Okay, what do we get when we plug 6 in?
36 times 36, don't know. 36 times 6, don't know. Times another 8.
Jesus.
36.
Give me just a second.
6 times 6. 36 times 36.
Just use the calculator.
Yeah, sorry.
I'm getting there. Negative
Or if you're determined to finish.
437.
400. Jesus
Big old number.
You got what?
Christ. Negative 437.
I didn't know.
As the final answer, negative 437.
Oh, it's because I haven't done that.
I say, if you're still doing 6 to the 4th and that's all you've done, you've still got more work.
Yeah. Yep.
Have fun with that. More
Nice.
power to you. I'm moving along.
437.
Okay, now, second derivative test means we're going to have to find the second derivative.
So let's split this 40 times.
Now, second derivative test. The idea of the second derivative test, we want to take each of our values and see what's happening here. Okay, so I want to know what's happening at the second derivative with the critical value of 0 and what's happening with the critical value of 6.
Calculator.
I got this one, don't you worry.
I'll take 0 again.
0.
144.
So, the second derivative when x equals 0 is 0, correct? What is the second derivative when x equals 6? 144, which is what type of number? Positive. A positive second derivative indicates concave up. Okay? So, find relative extrema for each function. With this in mind, what's going on at 6? If this is concave up, it's a minimum. Does that make sense? Concave up is going to have a minimum. So, one thing I can say here, I'm just going to, local or relative. We can't say absolute. We don't have that information. A local min occurs at x equals 6. And is, what is the y value? The local min is actually negative 437. And why is that true? Because the second derivative is
Less than, greater than 0.
greater than 0. And I guess I could say, and thus, G is concave up. Okay? So you have to think about what your second derivative test, we don't use it nearly as much. You have to think a little bit more. Okay? A positive second derivative means concave up. That doesn't mean there's a max. It means concave up, which is actually going to result in a minimum. Okay? Now, we also have a 0 here, yes? Our second derivative is 0. So based on the second derivative test, we're going to say no conclusion. Okay? More likely than not, I would expect it to be a point of inflection, but we haven't tested that information. Okay? So what I'm going to say about this one, whoops, I can't spell. Okay, no conclusion about x equals 0 since g double prime of 0 is equal to 0. And what I will say, likely a point of inflection, but were they asking me to find points of inflection?
No.
No, they're asking me for relative extrema. Okay, and I think if you graph it, it is a point of inflection. Yes?
So for, you're talking extrema for critical values, is that first derivative or second? What's the inflection is second?
General rule, yes.
Okay. So I noticed on the last page, we use the second derivative to find our critical point for values.
Yeah.
That we use first. So I was
I'm going to
trying
say general rule, yes. There are oddities, exceptions, but that's a general rule of thumb. Okay. B, you can thank me later. We're skipping the trig one.
The babbling.
to
Yes. So, where am I at? Okay. Let's see what we can get through in the way of 8 and 9. We're making good progress. We're not, I don't know that we're going to get through all of this.
Which one's trig?
The one we skipped.
7B.
Oh,
We skipped 7B.
we're gonna skip 8.
And we'll probably be skipping 9 at this rate just because I can't work miracles here.
I don't even think we're gonna make it through this whole one.
I know.
Sorry.
I'm already thinking that, so. Okay, the graph of f prime, the derivative is shown. Always, always, always take a moment and assess. What is this a graph of? It will always tell you.
F prime.
That is f prime. You're going to have to think differently here, right? Like we have to stop and think, okay, this is f prime that is right here. On what open interval is f increasing?
Negative infinity to
A,
A.
and then B to C.
Why?
Because f prime is positive.
So we're looking at the derivative, yes? This is the derivative. But what are they asking me a question about? The original function. So you're not looking for where is my graph increasing here, right? We're not looking for the fact that this graph is increasing from -1 to 3. That's the derivative. That's not what I want to know right here. We're looking on the fact of when we're asking when is f increasing? When is the second? Nope. First derivative greater than 0, aka positive. So when is it positive?
Negative 10D.
When it is above the x-axis, right? I can't even write that in there. Well, I can try, I guess, but. So when f prime is greater than 0 there and there. So it is indeed from negative infinity to A and B to C. And I guess what I have written in mine is f increases where f prime is greater than 0. Because I guess it did just say justified, didn't it? Whoops. F prime increases where f prime is greater than 0. And that's happening on negative infinity to A and B to C. Okay, we good there? Okay. B.
A, B, C.
At what value of x does f have a local max or local min and justify? First of all, in general, what were you looking for?
0.
When the derivative equals 0, yes? That's in general what we're looking for here. Now, so the key points were at A, B, and C, because at those points, that is where the derivative equals 0. That correct? Now, I am going to take us a step farther. I know it doesn't specify this. Well, I guess it's a matter of how you interpret the question. But I want to go as far as saying, of A, B, and C, what are mins and what are maxes?
I think A's a min because it's on the
No, A's the max.
negative side, but that's just a guess.
A, the max.
Notice that.
Because it's going from increasing to decreasing.
Yeah.
Okay, I'm having us think sign chart here. Okay, but it's going to be, if you're erasing, that's great. What do you notice about the first derivative to the left of A? It is what?
Negative. Positive.
It is positive because it's above the x-axis. What do you notice about the derivative between A and B?
Negative.
It's negative because it's below the x-axis. What about the derivative between B and C? It's positive because it's above the x-axis, and the derivative to the right of C is negative because it's below the x-axis, correct? A positive derivative indicates that my graph is increasing. Negative derivatives indicate my graph is decreasing. So at A, we change from increasing to decreasing, which is a max. At B, we change from decreasing to increasing, which is a min. Are you following?
Yeah.
And at C, we're changing from increasing to decreasing, which is a... Are we there? Okay, now, some of you saw that without the chart, yes? Awesome. I needed to make that connection to make sure everyone saw it with me. Are you going to have to use a chart every time? Not necessarily, but. Okay, so I'm going to say F has local max. I guess that should be maxes. I don't know how do you write that, but local maxes at x equals A and
X equals C.
x equals C. And why? F prime changes from positive to negative. This is where I really would have been beneficial to zoom this in more, but you guys have plenty of room on your paper to write. We also need, F has a local min
At X equals B.
at x equals B, since F prime changes from negative to positive.
I think maxes has an
I know, I debated how I should write that because I don't know.
I love to like that.
Make it whatever you want. I don't care.
The inflection points of F would just be A, B, C, right?
No.
Oh, well.
A, B, and C are mins and maxes.
Is it those?
We haven't touched this.
Okay, so inflection points of F. It's where the second derivative equals 0. This is a graph of the first derivative. What is the second derivative in relation to this graph?
It's
Right there.
the
It's
same
tangent lines.
It's the same.
It's the
relation.
tangent lines, it's the slopes.
Yes.
Yes? So when we look at this, we're looking for slopes. Inflection points are going to happen when second derivative equals 0. Where is the second derivative equaling 0 here?
On the given.
Negative 3, 2.
Okay? So there are going to be inflection points. Now, -1, -3, and 3, 2 are not points from the original graph. We just want the x values there. Does that make sense? Okay, so F has inflection points at x equals -1, x equals 3, and that is because second derivative equals 0. Okay. Concave up and concave down. Well,
A to B is concave up, B to C is concave down.
That's on the derivative. You gotta get the second.
Oh, dang.
we got to talk second derivative here. Okay, so, and this is where from -1 to 3, or -1, 3 are my points. This is a second derivative. To the left of -1. What is my second derivative? It is a, what is the slope doing?
Decreasing.
It's a negative slope, isn't it? It is decreasing. So that's going to be concave down.
From 1 to
From -3 to -1.
I know. It's
Okay,
sorry.
from -1 to 3, my graph is increasing. So it's a positive second derivative, which is concave up, decreasing, concave down. So you see your concavity, your pros, and you could write that out, right?
Yes.
Okay, we don't have time. Man, can you sketch the graph of f of x? That would have been a good one.
X to the fourth.
Okay, so tackle homework. Okay, tackle homework. See what you can do with it. I will say we're supposed to start 5.5 notes tomorrow. However, I may mix things up again because I'm not here on Thursday.
What? Oh.
So we're supposed to start 5.5 notes tomorrow and finish them on Thursday. I may try and do the bulk of, I may try and spend more time on that than checking homework tomorrow and save homework for questions for another day. So we'll get there.